What's cracking, guys? Aleksa here. In this video, I'll be walking you through the code base behind the recent OPT-175B transformer from Meta. And if you're curious to learn about the actual theory, about the paper, I covered this paper as well as GPT-Neo X20B and as well as Big Science Blue models. So the corresponding papers in the previous video, so I'm going to link the card somewhere up there. In this video, I'll be walking you through, as I said, through the code base behind the OPT model. Basically, that's the metaseq code base. And my idea will be to first show you how to set up this on your local machine, because the system was designed, the code base was designed to be run on a Linux distributed system. So that means multi-node, multi-GPU setting, whereas I have a Windows single GPU machine. So that kind of made it a bit harder to get started. So that's the first thing. The second thing, I want to show you some of the concepts I introduced in my Ultimate Guide to Scaling video. I'm going to link the card as well somewhere here. Basically, I'll focus on the mixed precision training, and I'll show you some of the concepts such as loss scaling, etc. And also you'll just get to see how this not production level, but like a code base behind one of these large language models looks like. So hopefully that's going to be valuable. Okay, let's get started. The first thing we need to do is open up the setup guide. So there is the setup instructions here, which we're going to follow. It's fairly straightforward. There's a couple of caveats, but that's pretty much it. So I'm going to open up my Anaconda prompt here. I'm going to first create a Conda environment. So Conda create name. I'm going to use opt2 because I already have opt environment set up. So I have to change the name there, and I'm going to use the Python 3.9. So I'm going to hit enter there, and this will be quickly over. And once we have Conda installed, we'll start installing the necessary packages directly inside of it. Okay, this is going to be quite fast. So activate the environment, clear, just to clear the screen a bit. And now I'm going to just copy paste this command here. So we do this pip install of basically Torch and Torch Vision, etc., etc. So just hit this command, and that should execute in a couple of minutes. Okay, guys, so that's installed. Now let's continue. So the next step would be to install the Apex library from NVIDIA. Because I'm on Windows, this does not work. Windows is not supported. So you can follow these steps on your own. If you're on Windows, just skip this part. There is a bit better instruction for how to install Apex in case you have some mismatch of the CUDA versions, etc., etc., and like some basically tips on how to overcome those potential problems in this Big Science repo. I'll link that link down in the video description so you can check it out. So I'm skipping the Apex. Let's now continue on installing the Megatron. So let's just copy paste this part here. Well, before that, sorry, let's just first clone the actual repo. So I'm going to do the following. I'm going to just create a directory here. I'm going to name it opt. I'm going to just do a clone operation inside of that directory if I manage to open up the folder. So here's the git bash. Just go and basically copy the link, the URL, do git clone here, and that's going to download the actual metaseq repo in this target directory. So once we're there, let me just navigate using my environment. So I'm going to open up this thing here. I'm going to navigate here in the console to the root of my code base, and now I'm going to follow the rest of the instructions. So let's now do the git clone. So let's do the Megatron installation. You can just copy paste this directly in the terminal. Everything is going to execute automatically except for the last line. So hit the pip install command here. That's going to install the Megatron, hopefully fairly quickly. Yeah, okay, that's cool. Let's continue on the second step. Now, important thing you need to do here is just go back to the root to metaseq, and you don't want to install inside of the Megatron the fair scale library. So I'm just gonna copy paste this again here. We're installing the fair scale, and I hit pip install for the last line, and we'll install the fair scale as well. So it's kind of smooth so far. No problems here. Okay. Finally, because we've already installed, we already cloned the metaseq, we just need to go to the root, so change directory to the root, And now we do pip install. But before that, there is a additional tweak I have to do, and that's in the setup file here. I have to basically open up this file and find the AIM library. And this one also doesn't work on Windows for whatever reason. I just didn't want to hustle around it, so I just kind of commented out, and that's it. After this, you can hit the pip install command, and everything should work as expected. Let me paste this, let me click enter, and that's going to be installed now. Okay, there is one more command we have to execute, and that's not in this manual, so that's this pip install setup tools, this version 59.5.0. There is some weird version error going on if I don't do this, so I kind of found this on some random website as a solution. And finally, this is not necessary unless you want to like basically contribute to the repo, this pre-commit install, but let's just do it either way. Okay, cool. I'm gonna clear the console here. Everything is ready now. Now let's open up the actual code. So I'm gonna use VS Code as usually, VS Code here, and I'm gonna just do the open folder, find this metaseq directory, and just select folder. That should be pretty much it. So now what we want to do is select the correct interpreter, and that's the OPT-2. So let's just open something. Let me open up some of the files we'll need a bit later. So this is going to be the training file. Let me hit the, nope, I don't want that. So I just want to hit the Control-Shift-P, select interpreter, and let's select the OPT-2 interpreter here. And that's now it. The final thing we have to do is a couple of patches. Obviously, I had to sort it out before the video. So let me just show you what those are. I have a working code here, so I'll just do git diff tool to show you some of the differences, some of the patches I had to apply. So first thing was, and we've already done this, is to comment out the aim. This might not be necessary for your case, but just like that's something that I had to do. Okay, then there is this line in train, so I'm just gonna copy paste this one. You obviously won't have to do this because I'll basically create a clone directly and push it to my GitHub. But let me return here. So this is something we have to add basically here. I'm gonna just save it there. Then let's see what else. So let me exit here. We have a couple more steps. Metaseq tasks base task. We have to add this weird line to convert it to long, otherwise it's gonna complain. So that's the base task inside of meta tasks. So let me open up that file. Again, you can skip this, all of this, because you can just start from my code. So I'm gonna do this. So metaseq, find the tasks, find the base task, and find this line. So this is basically, let me find this thing. So filter, filter examples, blah, blah, blah. So it's here. So I just paste that line here. It can be cleaner, obviously. I'm just doing it like this, like you should import it on top of the file, but this is just, the whole point is for me to enable this code so that I can easily run it and do stepping through of the code base. Okay, so I think that's one step. Then we have the sweep. We can actually skip this part. We don't have to do this. Then there is this thing. So we have to change from 2 to 1 because I only have one GPU. Otherwise this will fail because, as you can see here, this is the model parallel argument. So I'm just gonna do that. So that's metaseq launcher opt job constants. I'm gonna just patch that quickly here. So let's go to the metaseq launcher. So metaseq, here's the launcher, here are the constants, and we just put ones here. These are the smallest models. You can see the 8 million, the 125 million, and the 350 million, the tiny, small, and medium ones. Okay, and the final thing we have to do is in the opt baselines, we have to comment out this if args number of GPUs smaller than 2, then raise an error, because obviously I have just single one, so I'll have to do that. And there is this one here with the environment thingy. So it was obviously a lot of trial and error to get this like sorted out, but yeah. Okay, let me find the opt baselines. So args num of GPUs, here it is. So I have to comment out this line, and the final patch that I have to apply is this one here. I'm just gonna do copy paste of this on the bottom of the file, and that's it. Okay, guys, that's pretty much it. Okay, having done all of this, let's go back to the repo, and now we want to train this thing. So let's see what the instructions say. So they have this training link here. You open it up, and the only thing you have is this. So from here, I had to work my way around and figure out what's going on. So let's see what I'm gonna do. So I'm gonna instead just copy paste the launch arguments I already have in my code, which I've already previously been running. So I'm just gonna copy paste all of these arguments here, and you'll see what's the difference basically. Let's just give me a second here. So I'm gonna open up this one, opt baselines. I'm gonna create basically a config file here for running the code, and let's just paste those arguments. So let's see what's the difference between this thing and what they show here. So first things first, you can notice I have the benchmark and the local. The local makes it so that I can run this on a local machine, obviously, and the benchmark was necessary to basically so that you can skip downloading big data sets, and this will just use some dummy data loaders, and everything else will stay the same. So that's kind of cool. Okay, so number of nodes was obviously I had to change it to 1. It was 2 here. And number of GPUs, I had to set it to 1 instead of 8 here. And other than that, everything else remains the same. Okay, so now let's run this code. I'm gonna zoom in a little bit here, and I'm going to set a breakpoint here, and let's just run this code. Okay, let me run this, hit run. And the whole point of this script will be to collect the arguments that then we are going to use for the train script, because they don't have any instructions for how to start the actual train script. So this is a workaround I kind of figured out. Let's see what's going on here. So we have to go here and then sweep main. So this is maybe helpful for you to understand my process, and then basically in case you need to figure out something on your own, you can follow a similar workflow. So we end up here. Then we enter this backend main. I'm gonna put a breakpoint here. Let's just continue. The whole point was to find, so let's continue here. The whole point was to find the actual command line that's being used to call the train script. So we'll see how that looks like in a second. Okay, let me do this. Let me just find so train commands. We don't care about this code. We just want to find the final code that's gonna be run. So I'm gonna put breakpoint here, hit F5. Let's continue here. Let me just find, local run. So this is where we want to go. F5, enter the local run, and here it is. So here is the actual piece of code that will call the train script. So we have this train command. So it's Python, blah, blah, blah. It's calling, as you can see here, hopefully. Let me just see whether I can shift this. Okay, so what I'm gonna do is this. I'm gonna open up the debug console here, and I'm simply going to capture all of these arguments, which we will then use to run the train script. So we don't care about this env thingy. We only care about the actual commands that were passed to the train script. Okay, you can see here Python, blah, blah, blah. It's calling the train script. So this is the thing you can do. So with open, basically command take txt, and then write mode as F, and then we basically want to write to that file this train command. And this is going to obviously save this command and capture it. And so I'm going to do that, and let's see what's going on. Okay, so we've saved that somewhere here. Hopefully, commands, and then you can just copy paste all of these and start playing from there. So that was my first part of the process. So it took some time to figure out how to call the train script, and this was my workaround to get the actual commands. And then came the tweaking part. So I'm gonna just again kind of speed this up by copy pasting the actual arguments. You can see it's super duper verbose. I'm gonna copy paste all of this, and I'm actually gonna copy paste everything, including these comments I made here. so that I can explain what I've done. So let's go to the code here. Again, you will not have to do this because you'll have this already on my GitHub repo. Okay, let's go here. Let's rename this as opt baselines, and I'll have to create another config here. For the train run, I will just add configuration, Python file, and then I'll just add the arguments here. Okay, that's it. Hopefully, if I haven't made any mistakes here, we don't need this, and that's pretty much it. I'm gonna rename this file to this config to train script, and let me show you what's going on here. So a lot of arguments. Obviously, this is what you get when you're working with large language models, and in general with libraries such as metaseq, which is, I think, cloned and then modified version of the fairseq library. Okay, so this is pretty much the same thing as what we get when we run the previous script, with some modifications. So some of those modifications I had to make was like I can't use fully sharded because I have a single GPU. I can't use the parallel version of cross entropy, so I had to kind of change it to cross entropy instead of cross entropy parallel or something. Transformer LM instead of Transformer LM Megatron or something. And finally, Windows was complaining, I guess any operating system will complain about super long paths. So there was some super long path that we get dumped from the previous script, so I had to kind of shorten them into this one. So test v0. And finally, I had to remove the checkpoint activations and distribute checkpoint activations. This is not, well, it's actually necessary, otherwise you will face some bugs, but like I didn't bother to try and figure it out. So if you want to kind of play with the checkpointing, which is the technique where you basically trade off the memory versus the speed of your backward pass, then you can kind of enable this and try and figure it out yourself. But like I'm going to focus on the mixed precision part of the code. Okay, made a couple more tweaks. You will be able to just copy paste this. Okay, I think a couple of things I had to change was like the batch size, because otherwise I was getting OOMs, out of memory exceptions, and I had to change to like have 128 tokens per batch. Per sentence instead of like 2048 by default or something like that. But that's it. Again, you'll copy paste this thing and you can start from here. Okay guys, let's finally get to the train script. Let me set a breakpoint here. Let me use the train script config, and actually I'm gonna set another breakpoint down below here. And now we are ready to run. Okay guys, let's start going through the code here. I'm gonna focus on the, well, I'm gonna show you details that are different compared to your toy repos, so to speak, because this is, after all, using this fairly powerful library that was developed by Meta. So yeah, there is a lot of code that makes this harder to read, but like more robust to various errors. Okay, so let's continue here. So first things first, I'm gonna enter this parser function, and I wanna focus on a couple of details. Like, first of all, I think it's quite kind of interesting how they are picking up various arguments. It might not be the most readable way to do it, but it's interesting in the sense that, let me show you what I mean. So here, there's this common config. So common config will be just a data class that contains a bunch of these fields that basically define various variables which belong to the common group of variables, of arguments, such as logging interval, TensorBoard logdir, various thingies like this aim repo, so that's this visualization tool. Then there's the weights and biases project here, Azure ML logging, a bunch of details. So yeah, I won't focus on those, but I just kind of want to stress that that's neat. So once we basically execute this line, we'll pick up all of the arguments and default values from this config. Okay, next up, they have these registries. So this is probably less interesting. Let me just see here. So yeah, they are picking up values automatically. I mean, I'm gonna skip this part because otherwise this will take too long and it's not that vital. So bottom line is Now the same thing will happen in all of these other functions. So this is, if you enter here, you'll see that there is this generate parser from data class, and then there is the dataset config. So here is where they define some of the default values for the dataset group, and then so we can basically continue. Let me just go back here. So yeah, by the way, if you don't know how to use VS Code, there is this nice call stack like a window here. You just hit the whatever is on top of the stack, and you get back to wherever your debugger has stopped. That's kind of neat to know. So again, bunch of different groups will add different arguments, and finally we end up with a parser, and that's it. Now some conversion to config, so it's going to be a dictionary or something. And now, because we're not profiling, we're not doing this, we won't enter this branch, we're going here. So let's enter the actual main function. We can skip all of this, and we enter the single GPU main branch. So the only difference is, well, there are some differences, but ultimately all of the code paths, whether you're running this in distributed setting or on a single GPU, will call the same main function. So that means we'll be actually stepping through the actual code that was used to train the huge OPT-175 billion parameter model, which is awesome. So let me just show you quickly this thingy here. Again, there are many details here that are relevant if you're running this in a distributed setting. That might be interesting for you to check it out, but here I'm going to focus on this code path here. So let's enter the main, and let's keep on stepping through this. So let me see what's interesting. So here, this is the patch I applied. So finally we save the config. So this is the config that we got from all of those parser steps. So ultimately we just save it here to config YAML, and we'll see how the config looks like. Okay, let me just now show you how this thing is going to look like. So this is hopefully the right, this is the right directory. So let's open up the test v0. Let's open up the config. I'm just gonna basically open up another Visual Studio instance here, and let me open that file. So let's open the file here, this one, and here's the config YAML. So I'm going to open it up here side by side. Okay, so as you can see here, there is a lot of arguments, like I think over 400 or something, like a huge amount of arguments. This could use some cleanup and refactoring, but I guess it works, kinda. They did struggle a lot, so I don't know. Cool. So I won't be going through the arguments here. Obviously, it beats the purpose. There is too many things going on. So I'm just gonna explain you those that we are hitting as we are executing along this code path. Okay. So there is this nice is master function. I think it just checks. So because the distributed rank is equal 0, so rank means basically if you have multiple GPUs in a node, rank 0 would be GPU 0 in that node, rank 1 would be GPU 1, etc. Just like basically naming for your GPUs in the node. Because here we are 0, because we are running a single GPU, we are going to be the master because we are the only GPU, so we are the master automatically. Okay, let's continue here. I'm going to skip all of that, just some asserts, ignoring all of that, seeding the code so that we can have reproducibility. And then some additional seeding that kind of probably in the background, I think it just seeds the torch thingies. Yeah, torch, manual seed, blah, blah, blah. I'm going to skip those details. Verified checkpoint directory. I think this is kind of neat. So again, this video, I'm just showing you some details that go into the engineering behind these LLMs. Is not only like the actual ML logic, that's what I'm trying to get at, is super simple. Like you have a transformer, you do everything, you can literally write all of this logic conceptually in maybe 100 lines of code or something. I might be exaggerating, but the point is there is so many things that you have to add to make this robust and to make this work on such a large scale. So this is one of the details. So let me enter this. I'm gonna put a breakpoint here, hit F5. Okay, so let's see what they're doing. So they are literally testing if this test v0 directory exists, and we actually have the access, the rights to write to that directory. So if it exists, if it doesn't exist, we create it. Because it does exist, we don't create it. We fetch the global rank. It's going to be 0, I assume, because yeah, as I said, we create the temporary file. So we just create some random file here, and we try to open it up in a write mode. That shows us that we have write access. So as you can see here, we're not hitting the exception, so everything's fine there. And finally, we try to remove the file, so you can see here. So if I were to go here, there is the dummy file. And now if I go F10, so step over, you can see how this thing is deleted. So that's how they do the check, that you can actually write to that directory, and that's robust. Okay, now some logging, how much memory I have, etc., etc. Logging the whole config. You can see there is a bunch of data here. Everything we saw in the actual YAML file in the VS code. And yeah, okay, I'm gonna skip this. There's the setup task. I'm gonna enter this part of the code as well. So let's see what's going on there. Blah, blah, blah. So we have the task name that's called dummy LM. This is a consequence of me using the benchmark flag, if you recall. And yeah, so that's gonna be like a super simple task. We're gonna see what it does in a couple of seconds. So here, we just pick some basically associated config with that task. I will not get into how they populate these. There is a neat method they use in the background. Well, I'm not sure whether it's neat. It's kind of hard to read and understand, but again, it's understandable. Let's enter this one. Let's enter the actual constructor of the dummy LM task, and here we are. Okay, so let me see whether it's interesting to see the base task. I think nothing there is yeah, okay. So I'm gonna just skip the init function of the base task, and let's see how this is gonna work. So we create a dictionary, and this dictionary is just gonna be adding a bunch of symbols to this task, which is not important. It's gonna add like 50,000 or something 51,196 symbols. These will not be important for the training, as you'll see in a second. And then what they do is they pad to multiple of 8. So why do they do this? Is because sometimes on the hardware, on the underlying hardware, if things are divisible by 8, things go much faster. So that's a constraint that you kind of have to know of the underlying GPUs you're using. So I guess NVIDIA A100s or H100s, the new ones. So yeah, again, details that matter when you train on such a large scale. Okay, and finally what we do here is we create, as you can see here, 128 basically numbers. We add +1 because here we'll create, one will be the source sequence, and the second one will be the dummy, the target sequence. So that's basically your transformer logic. You have a sequence, and then you shift it to try to predict the next token, and that's why you have here, you grab the first 128 elements, and then you grab you move by 1, and then you grab the 128 there, and that's what you're trying to predict. Hopefully that makes sense. There is additionally some logic here, which is not necessary for this dummy task, but in general, what it does is make sure that you're not predicting the padding token. So that's why you have this, but it doesn't matter. For now, that's enough. Okay, so that's the setup task. As I said, super simple. We just have these 2 dummy sequences that will be later passing through the transformer during the forward pass. Okay, because we're not sharded, I'm gonna skip all of this, but you see that if we were running this on an actual distributed system, we'd be hitting this branch instead. And you can see there's this FSDP wrap that helps with the model training on a distributed system, basically. Okay, build model. I'm gonna enter this branch as well. Let me see what's going on here. So build model, we are using the transformer LM. Again, I cannot run the Megatron version because it assumes I have at least 2 GPUs, and because of that, I'm getting basically exceptions if I do this. So let's just pick up the model. The actual class is, so this is what this registry thing does. It takes the string transformer LM and picks up the actual class that we'll be using to instantiate the model. Okay. And then here it just picks up the associated config. So transformer language model config doesn't matter for us at this point of time. Let's enter the build model branch and let's see what's going on here. So we first build the embedding table. Okay, so that's the first part. So that's how transformers work, right? We have a piece of text, a sentence. We tokenize it into a bunch of integers. which are usually of a long data type. And then we use those integers to index into this embedding table to extract a particular embedding vector. And then we're going to feed those vectors through the transformer. That's what this thing does. Okay, I'm being a bit more detailed than in general because, yeah, I think it makes sense to do it now. Let's see how this is going to work. They call some embedding thingy here. And once you enter there, you see that ultimately it boils down to PyTorch embedding. So we fetch the device here. It's going to be CUDA 0 because we have that's the index of my single GPU. Because this is set to true, we'll be using half precision. So everything's going to be in half precision. So you can see here what we do is number of embeddings is 51,200 because that's the, if you recall, that's the dictionary size. So that's the, even though we're using a dummy task. Then we have embedding dimension, which is 512. And we are running this on a GPU in half precision. So that's float 16. So let's create this empty tensor. And then we just basically initialize it normally. And then I'm not sure why we're doing this. Basically what they do is they set the padding vector to be all zeros. So currently, if I were to open up this one, let me show you this. So if I use the weight of padding index, and if I do this, you can see there is a bunch of values. After we step over here, now if I execute it, we'll have all zeros. So I'm not sure why they're doing this because ultimately embeddings are learnable. So yeah, I'm not completely sure what's going on. Embeddings constructed, we get back from the call and we are here. The next thing we do is we construct the actual decoder. So this is going to be a decoder only transformer. So let's enter into this thingy and let's execute. Okay. Let me see whether there's something interesting here. Incremental decoder. I think it's just going to store the dictionary so we don't have to enter the constructors of the parent classes. I'm going to skip over all of that. Let's focus on the important parts. Nothing fancy here. We're just storing some variables, blah, blah, blah. Okay, so the first thing that we're going to do is if the embedding dimension is different from the input embedding dimension, which they are, then we'll create this linear layer that's going to take our embedding vectors and just increase the dimensionality from 512 to 700 something. So let's see what it is. So we have a linear layer. So from 512, it's going to map them into 768 dimensions. Okay. We're not using a libby in this particular setup. So we can ignore all of this. We can ignore all of this. And let's see where we are now. So now we are generating the positional embeddings. Let me enter inside of there. So I just hit F12 to enter. I set a breakpoint here. I hit F5 and we are in. Okay, this is learnable. So we enter this branch here. Number of embeddings is going to be whatever the number of embeddings here is, plus padding plus 1. Because I assume it's for the beginning of sentence token or something. That's why they have to create 130 of these instead of 128. So remember, we only need as many positional embeddings as the longest sequence will be feeding to the transformer. Because we're using this dummy task, we're only feeding 128 tokens. So that's why we have this many positional embeddings. So then we call this learn positional embedding thingy, and that's just going to do what? Let me see. Well, it's just embedding. It's literally just a torch embedding again. So we can just skip over that. It's just going to create embedding table, and then we initialize it again. And again, padding index is set to 0, and we return back the embeddings. So that's it. Okay. Similarly to what we've done for the input tokens embedding table. Okay, so now we're gonna do this precision conversion. So we'll be grabbing the embed positions and we'll convert them to FP16 basically. So let me enter this function here. I'm gonna hit a F, like a breakpoint here, hit F5, and let's see what's gonna happen. So we assert that it's not B float 16, so it's the brain float format. Check out my, again, ultimate guide to scaling to understand how these formats look like, how they work. and why they're important. In a nutshell, it just increases the range, but I don't have BF16 on my machine, so we're just going to use the half, which is the FP16 format. That's has a smaller range, and that means it's the weights during the training and the gradients and everything is more susceptible to both underflow as well as the overflow. Okay, so we basically transform them to half precision, and we get back here. Okay, let's continue. Next up, we generate 12 of these decoder layers by calling the build decoder layer function here, and this one is going to be fairly interesting. So I'm going to put a breakpoint here, hit F5, enter here. Let's first build the base decoder layer. So I'm going to hit F11 to enter, F11 again to enter, and let's see where we are. So we are in the decoder layer. Okay, so we're trying to construct the first one. Now this part is fairly interesting. So this is something you don't see in a regular code base that's not super optimized. Here we'll be using Megatron fused kernels. Well, actually for this particular setup I will not be using these kernels, but still we'll see how they are loading them and how it looks like in practice. Okay, so let's go through all of this. That's not important. And now this part is interesting. So let's enter the fused kernels load function. F11, and here we are. Okay, so first we pick up some metadata about the CUDA. That's not that important. Let's just step over all of these, and then this one is fairly interesting. So this one is going to load certain kernels written in C++. That's going to be super efficient compared to running in Python. So let me just go here. So fused softmax, we just defined the function. This is set to true, so we enter this. We just create some flags, and you can see here we are now creating a path towards certain CPP file and this CU file, CUDA kernel file. So, by the way, I'm not super familiar. I've never had to write any code in any CUDA kernels myself. So yeah, just FYI. So here are the sources. And now we're gonna load those files using this CPP extension load helper. So this function here. So it's gonna load from those files. Let me show you those files here. So here it is. We have to enter the Megatron. We have to enter the Megatron again, and then the fused kernels. And here are those files. So we are scaled upper triangle mask softmax. So here it is. I'm gonna open it up. I think that's the one, and then we have to open up the CUDA one, right? So that one, let me just open it up with VS Code. And then there is this one. So let me open it up with VS Code as well. And that's the only two files I'm gonna open up just to show you how it roughly looks like. So here is the CPP one. So you can see here, they define forward and backward for this particular softmax layer, and they make it super efficient. So in this particular part, in this file, they just create a binding to Python so that we can execute a C++ code directly from Python. So here is the actual code behind that file. So here is the blah, 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 the backward CUDA file, and everything boils down to this dispatch half and bfloat function. Let me see whether I can do F12 and see how that function looks like. Yeah, I won't go there, man. That's gonna be wicked. In any case, this was just more of an FYI than anything else. I don't want to dig too much into the C++ code because that's gonna get like messy very quickly. Okay, let's go back to the let's find my prompt. Let's find the debugger, and let's continue execution here. So this might take a while. Just the loading of this, I'm gonna skip this loading part, and I'm gonna just hit F5 to get to the mask softmax here, and I will get back to you as soon as, yeah, here it is, because I've actually pre-built it before. But the first time you run this, it will take probably 5 minutes. In case it's hanging, there is one trick you have to do, and that's to just delete this build directory. Again, don't ask me why I know this. Yeah, the tears on my keyboard know it. Okay, let's continue here. Let's load these scaled mask softmax ones. And as I said, we will not actually be using them, but it's kind of funny to see that they are doing that. Okay guys, I actually realized that the actual implementation is in the H file. So if we open up this one, let me just quickly show you. So you can see the actual code, you can find it here. So this is how these functions are defined in the background, just a CPP function, C++ function, and the optimized version of that functionality. So yeah, let me go back now here. Let me show you one more thing. I'm gonna copy this, use the search functionality here in VS Code to find where this one is used. And you can see that, so we have init file here. Where it's actually being used is somewhere here. So let's just find it. Here it is. Let me try and see whether, yeah, forward affine. Okay, so there is this fused layer norm affine function that's inside of the Megatron library actually. And I think it relies on Apex potentially. So yeah, I'm just kind of showing you so that you know your way around this code. But yeah, so if we were to actually use this class somewhere in our code path, in the background, this part of the code would actually be C++ code. So that's kind of interesting. Okay, let's get back here and let's exit out of this function. Let's load this one, and then let me show you the creation of this decoder layer. So again, we are in the transformer decoder layer. Let's continue. We're building the self-attention. I'm going to skip that part because that's common knowledge, I guess. Let's continue here. Layer norms, initialize, blah blah blah. Again, we're converting the layers, the attention layers to flow. I'm gonna basically remove this one so that we don't have to enter anymore. So everything is being converted to FP16. So that's the mixed precision thingy. Yeah, let's continue here. We just fetch the activation function, which is going to be ReLU, I think. Yeah, and then let me just see what this one is. So yeah, you can see we're just, because activation was set to ReLU, we'll just return the FReLU, from the functional module we fetch the ReLU function. Okay, let's go back here. Now we create the fully connected layers. So we have obviously two fully connected layers in the transformer block. The first one is after the attention mechanism. We have the FC1, and then we have the FC2. No, actually, this is the I guess the MLP after the attention thing is gone. But like the actual attention logic also has the mapping, the linear mapping once you do the attention thingy with value vectors and everything, if that makes sense. So the reason they split up into FC1 and FC2 is because they use Megatron, and so I think that's some limitation that the Megatron imposes on the users. You have to kind of split these such that once you do the model parallelism, you can split these fully connected layers onto multiple GPUs. That's why they have to separately create the functions. So if that's confusing you, that's the answer. Okay, so it's just gonna build in the background. As you can see here, it's just going to build a linear layer, but the reason they're doing it like this is again model parallelism. And those are all of the details you kind of have to deal with when you're working on large scale. There are details that you kind of have to learn, and yeah, it's kind of different compared to small scale. Again, conversion to FP16. Let's exit here, and that's the base layer. Let me skip over all of this. And now, additionally, if checkpoint was set to true, we'd basically wrap this layer inside of the checkpoint wrapper. And again, that's what it does in the background is during the backward pass, you didn't store all of the activations, and instead you'll be recomputing the activations. And by doing that, you'll be obviously increasing the time it takes to do the backward. I think it's going to be 2x slower. But as a consequence, you save up a lot of memory because you don't have to save every activation along every layer. That's the checkpointing logic, but we're gonna skip it now. Let's continue here. This is gonna be no op, nothing's gonna happen in this one. And let's continue. Okay, so that's going to be repeated 12 times. I'm gonna do disable all breakpoints, put a breakpoint here, hit F5. Okay, and let's continue from here. Now I'm gonna re-enable all of the breakpoints, and that's it. Okay, guys, and we just pack those layers into module list. Nothing fancy there. Nothing fancy here. We have the project, again, projection, the output dimension projection from, I guess, 712 to 768 to 512. That's it. Okay, here, because share input output embed, it's set to true. This is one of the things you, again, kind of have to know, and that's that usually people tie the input embedding table with the output. And so here, instead of having a separate set of weights for this output projection, instead we'll just reuse the same weights that we use to embed our initial tokens. And you can see we're literally using this embed tokens, which is our embedding table. As you can see, 51, 200, and 512. That's the initial embedding table we created. And we're going to use those weights to populate this linear layer. So then you can imagine what this does is you take the output token, which is 512, and once you multiply it with this output projection, you end up with this 51,000 something, which is basically the vocab size of your output. Okay, hopefully that makes sense. Let me exit this. We are not using Alibi, so we can exit this. We have our decoder. We have the embedding table. That's it. Model constructed. Okay, now we have the criterion. We're using cross entropy. I don't think this is anything super interesting. Let me see what's going on here. We can skip all of this. We can skip all of this. Let's enter the builder. I think we can skip all of this as well. Nothing interesting here. So here's just the cross entropy criterion. I'm gonna skip all of this. This is not interesting. Okay, so now there is some logging going on. If you open up the terminal here, you'll just see what those logs are. It's just logging various stuff. So we're using dummy LM task, we're using transformer language model, we're using cross entropy as the loss. Let's continue. We are counting the number of parameters. Here we have 112 million. Blah, blah, blah. Let's continue here. Now we'll load the data set. So let's enter the data loading part. So I'm gonna hit F11. Here we are. So let me continue here. Okay, so what's this? Batch size is 1. As I told you, I'm using 1 because otherwise I would be hitting out of memory exceptions. And now we just construct a dummy data set. So here's how it looks like. This one, we basically just stored the batch. It's a super simple, well, literally dummy data set. The name says it itself. So what we do is we just create this batch. You can see here. And what we do is we have source tokens. We just have the array of 128 elements we created, if you recall before. So we just use that as the source tokens, and then we set as the target tokens those dummy targets, and you can see they're shifted by 1. So here we have 3, 4, 5, and there we had, for the source one, we had 2, 3, 4. So they are exactly shifted by 1. So this is going to be our simple dummy data set. We just have number of sentences is 1. We only have 128 tokens, blah, blah, blah. So we literally have batch size 1 and only 128 tokens. As simple as it gets. As simple as it gets. So let me just construct this thingy. And that's it. So that's the construction of the data set. It's very easy and simple. So now the trainer is just a abstraction they use to store everything inside. So the task and the data set and everything. So here they extract the shared parameters because I told you they're binding the input embedding with the output embedding, output projection layer. Again, that's now less interesting. I'm going to skip over all of these. They're storing the criterion, the model, blah, blah, blah. They are basically, again, casting to half precision, float FP16, both the model and the criterion. And now they're pushing it to the GPU. And that's it. Nothing interesting there. I'm gonna skip all of this. I'm just gonna put F5 somewhere here. Sorry, put the breakpoint and hit F5. My brain is glitching. Nice. Okay, so again, it's now fetching the environment for some reason. So you can see here I have RTX 2080, 8 gigabytes, 7.5 are the major and minor. And they just store that for whatever reason. I'm not sure why they're using it, probably just for the logging purposes, so they know exactly which devices, in case you have heterogeneous distributed system where you're using multiple GPUs. Some are maybe P100, some are maybe M40, some are maybe V100s, some are A100s. So you want to have that additional, as you can see here, they're just logging everything basically. Okay, we're back to the train. This is the main function, in case you're confused where we are. So let's now, I'm gonna skip this because this is just gonna give us back this iterator. And there is like literally 4 layers of wrapping they do here. They have some counting wrapper and then this wrapper and this wrapper, so it gets very, very unwieldy very quickly. So I'm gonna skip that part and just focus on the train loop now. So here we are, here's the train loop. Let's enter the train loop. Okay, so we're actually hitting this aggregate function. I'm gonna show you what it is. So I'm gonna hit F12 to train. I'm gonna put the breakpoint here. You can see there's this wrapper they're using, this decorator aggregate. And that's just going to make sure that when they're logging something inside of that scope, that all of those logging details are being stored into this particular train dictionary. And then they'll have multiple of these aggregate decorators, and that's just gonna like nicely organize where each of the logs is going to, so they know exactly from which part of the code which logs came from. That's the basic idea. Okay, so we're gonna just hit F5 and exit this and hit the initial part of the train function. Let's just grab the iterator. I can skip over all of this. Basically, iterator is just, as the name suggests, counting iterators. So it's just gonna feed us those 128 tokens on each call. That's it. We grab some progress bar. Again, I'm gonna skip all of that. Again, I told you this is how the code looks like when you're training bigger models. Like, there is a lot of things that you don't care about because they're conceptually not important, but then again they're super important if you want to be able to debug things when they go wrong. So I'm gonna skip over all of this. Let's get to here. Here is the actual train function. So there is train instead of train instead of train. Again, a lot of layers of kind of complexity. Let's skip over all of this. So here's the definition of the train. We hit F5, we get here, and this is where the actual magic starts happening. So we're now gonna iterate and fetch the sample. We will not enter this particular branch because this new profiler is set to false. And so we'll just hit this branch here. And now I'll hit the F11 and enter this train function. And inside of this train function, there is yet another train function. So let me hit F5 and we end up here. So we end up here, train step. So again, the outer train is the epoch train. This one is the batch train. This one is going to be like the batch train. So we pass just the samples and we do a single forward pass. So let's see what the samples are. Samples is a dictionary. As you can see, we have all of those tokens from the dummy dataset loader. 2 interesting things to notice. Again, they have this aggregate thingy going on. It's kind of convenient, might be confusing if you're not used to it, but it does the job. And secondly, they have this profiler record function. So what this thing does is, first of all, they enable the profiler. I'm going to show you that in a second. Secondly, this record function basically names this particular part of the code with train underscore step dash some number of the iteration. And that's useful because later on, when you analyze the profiler output, you'll exactly know how long or like you have the details, the profiling details about this particular piece of code. That's why they do it. That's why they have the record function here. So again, the profiler should have been set up somewhere here. Let me just see. Yeah, so when we were here, there was the profiler call here, and you can see profile memory true, with stack true, record shapes true. So that means they'll be profiling the memory. What was the memory footprint like? In case they are hitting OOMs, this helps you debug it. Recording the shapes of the variables, and also stack, if I recall correctly, yeah, I forgot what that command is. You can always enter the profile here and see what the stack means. So let me just find that variable. Okay, record source information, file, and line number for the operation. So additional metadata for the operations. Let's go back here and let's enter the train step. Again, I'll have to, it keeps on entering these aggregate functions. That kind of sucks. So I have to enter the train step using F12, set a breakpoint, and then hit F5. So now we're here. So let's see what's going on. So we set the seed, we set the models to train, criterion to train, we call 0 grad, and I'll actually enter 0 grad, and there is a particular reason I'm doing that. Let me show you why that is. Okay, let's enter this one. Let's enter this one. Let's enter this one. Oh my god. And here it is. So the reason is we have this loss scaling, and that's because we're doing mixed precision. And so loss scale is set to 4. And if you recall from my video on, again, the ultimate guide to scaling, why they do this is because you want to shift all of the values such that you're less likely to hit the underflow in the FP16 precision. So this kind of shifts all of the values, and that's why they do 1 over. Well, they're doing 1 over 4 because the multiply factor is going to do the unscaling. So we'll see this is going to do the scaling, and the multiply factor is going to do the unscaling. Okay, we'll see that a bit later, but that's a detail I wanted to show you. So that's the 0 grad. Let's continue here. We grab the sample, we do prepare sample, which is gonna do 2 things. One is to push the CUDA, and the second one is to convert to FP16. Because of that, I'm just gonna skip. Let's enter the final train step. And it's happening inside of a task, which is kind of unintuitive. Why would the train step be associated with a task? Like this way of structuring the programming model is kind of weird and does not resonate with my mind. Okay guys, let me enter that one. I'm gonna hit F11, and here we are. This is the train step. Again, take a look at the stack here. Like, the stack is horrible. We have train step inside of a trainer, train step inside of a task, but it is what it is. It's kind of ambitious to try to explain this code on the YouTube. So yeah, I'm giving my best. So again, record function forward. So we'll know exactly the details of this part of code. We'll know how much memory is spent. We'll know the shapes. We'll know the lines, everything. So that kind of makes it easier to debug. Let's enter this, F11. Here we are. We do a forward pass through the model. We pass the net input. That's going to pass us the actual tokens. So here we are. We hit the decoder. We pass the tokens to the decoder. And now we call this extract features function. The extract features function is going to do a forward pass through the decoder transformer. I'm not sure why they called it like that. I mean, it's not incorrect to name it like that, but kind of weird. Extract features. Okay. Let's continue here. Let's enter the extract features. And instead of extract features, there is the extract features scriptable, and the reason why they do this is because of torch script. There was again some constraint that if you want to have optimization, you kind of have to do this, and it makes the code horrible. I think they kind of mentioned that somewhere here. Blah blah blah. I don't see it now, but yeah. A scriptable subclass of this class has an extract features method and calls super extract features, but super is not supported in torch script. A copy of this function is made to be used in the subclass instead. Okay. Let's continue here. Let's continue here. Okay, this part is not interesting. So the first thing we do is forward embedding. So that's going to take our basically tokens. So from 2 to whatever, we have 128 of those. And we are going to now convert them. We're going to map them into multi-dimensional space. So let me enter this part. So let me enter this forward part, and let's see what's going on. So basically we just call, yeah, this is the torch embedding. So it's just going to embed basically everything out of the box basically. Okay, so this was actually the position. Okay, we first embedded the positions. Let me see where is the actual embedding going on. Okay, so here's where we embedded tokens. So we embed them here. So now we have token embeddings. So let me show you this. So we have token embeddings. The shape of this thing is 128, 512. Let's see what's the shape of the positions. It should be also 128, but we have 768 here. So that means we would have a mismatch. So because of that, we'll have to first do the projection. Okay, embedding scale is set to 1, so this is kind of no up. We do the projection from 512 to 768, and now we can add positions on top of X. So that's the initial part of the transformer logic. We do the embedding, we add on top of it the positional encodings, and now we start doing the forward pass. Okay, let's continue here and let's exit. We're returning back the embeddings, the positions, and the combined embeddings and positions after we do the additional projection. Okay, let's exit this part. We are again in the forward pass of the transformer decoder. You can always take a look at here to figure out where we are. Transformer decoder, we're doing the forward pass. We've done the embedding part. Here we create the mask, the attention mask. So let me show you how it's going to look like. I'm going to kind of quickly walk you through this part. It's going to create this TRIU. It's going to create a triangular matrix. It's going to be filled with a bunch of minus inf, so negative infinity, and that's going to be used to create a causal decoder, right? So we'll just add that to the attention scores, and that's going to, after applying the softmax, you'll end up with tokens that can only attend to itself and the previous tokens. So again, here we create 128 times 128 matrix of zeros, then we fill it with negative infinity, and then we just call this function that will basically create a triangular mask out of this. So let me step over this and let me show you how this looks like. Here is how it looks like. Again, zeros, and then on this the upper triangle is minus infinities. Okay, let's continue here. We're not using LEB, so we can step over all of this, and we just return back that mask we just created. Okay, so that's the attention mask. We do some transpose here operation. So because we are batch, number of tokens, number of channels. Now we are number of tokens and then batch and then number of channels. Again, optimization detail that a lot of transformer implementations do. Okay, we just store some inner states, blah, blah, blah. Now we do a bunch of passes through all of the layers. We have 12 layers, and we are gonna do forward pass through all of them. I'm gonna skip the actual layer logic. That will be too much. I'm gonna skip it, but it's just classic transformer stuff. So let me exit this. Let me exit here. Let me just put breakpoint here, hit F5, and let's exit the transformer. We do some, again, now we have, again, let me show you the, so we now passed all of those vectors through the transformer, 12 layers in total, and we end up with the shape 128, 768. And so you see it's kind of messed up, so we just do the transpose operation again, and now we end up with the correct, the usual shape. Okay, that's it. And finally the projection, so we have 512 instead of 768. Let me do F10. That's it. We return the inner states, we return the attention, blah, 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 and we return X, which are the actual output embeddings. Okay, let's continue. That's that part, and now we call the output layer, and that's gonna project this into, I guess, vocab size. So yeah, you can see here 51,200. Let's continue. Let's continue, and that's the forward pass through the model. Now we compute the loss. I'm gonna kind of skip through this a little bit. So we first to get normalized probabilities. This is gonna apply the log softmax on top of our outputs here. Then we do some reshaping, and let's see the shapes. And those of you who are still watching, I'd love to hear your feedback. Like if you have any feedback, it would be super appreciated. So 128, 51,200. Whereas now these are normalized because we applied the softmax. Okay, so we get the targets. This is just gonna fetch those sample targets. So that's gonna fetch those 128 tokens that were shifted by 1 to the right. I'm gonna convince you that that's indeed the case. So you can see here, 3, 4, 5, that's the target sequence we were using the whole time. And now we apply the NLL loss. So that's the negative log likelihood loss. And you can see it's a bit more complex than your usual implementation. So your usual implementation would be just this. But when you're dealing with, I guess, like big dimensionality and a big vocab, then you can see here, they have this if branching. So if the number of elements is smaller than, what is this, like 2 billion, then you just execute this standard FNL loss. If it's not the case, then you have to do some a bit more intricate logic because otherwise you would encounter some numerical issues. So because we are smaller than this, let's see what the number of elements is for us. We have 51,000 and then dimensionality is 128. So I guess it's, yeah, it's below this threshold. So we just do this negative log likelihood, and that's it. That's everything. That's how transformers work. Like you just apply this NLL loss on the output and compare it with the targets that are shifted by 1, and that's it. The whole magic behind transformers. Okay, now here's where the actual mixed precision magic happens, and we are almost done with this video. I'm gonna quickly walk you through all of this. We're just like logging some outputs. That's not important. I'm gonna skip all of this. We're just storing some stuff, blah, blah, blah. We're just storing some stuff. Let's go back here. Let's return back the loss. So here is the loss. And now let's go for the second part. So this is the interesting part. So we do backward pass, and we again do record function backward to just profile this piece of code. And let's do F11 here. Let's enter. So now, because we have scaling, let's see what happens. So scalar is not none, so we enter this branch. And what we do is we scale the loss. Okay, so whatever the loss is, and it's 1,400 something, and it's that big because we were just doing summation in the NLL loss as the reduction method. So if I enter F11 here, you can see what we do is we simply take that number and we multiply it by 4. And that's what I previously explained you. Because of that, when you multiply the loss by 4, you trivially multiply all of the gradients are going to be multiplied by 4. That's how the chain rule works. So let's hit F10. Let's now do the backward pass. I don't think anything special is going to happen here. I'm just gonna, yeah, everything is, yeah, we exited the train step, and now let's go back. We're now level up in the train step of the trainer, not in the train step of the task. Let's hit F10. We just append the outputs, blah, blah, blah. That part is not interesting. And okay, let's continue. So here you can see this is kind of wrapped up inside of a runtime error out of memory exception, so that the whole training procedure is wrapped up in that. I think this is it. We just have a single batch. That's why we exit this for loop through the samples. And let's continue here. Sample size was 128 because we only had 128 tokens. This is some logic that would be necessary if we had multiple machines, which we don't, so that's fine. Okay, so we now enter this interesting part. And this is pretty much the end of the video. So try except. As you can see here, there is so many excepts they're catching. So they're catching the floating point error, they're catching the overflow error, they're catching the out of memory error. So all of these things are necessary when you're training at these big scales. You want to catch the errors, you want to handle them gracefully. So you can see here, if there's a floating point error, I think they do have this NAND detector. Yeah, we'll get to that a bit later. Let me now first walk you through the reduced gradients. So here, actually nothing is going to happen because we have a single GPU. Otherwise, you would take gradients from across the devices, and then you would do the all reduce. So that means you literally take all of the gradients, you push them onto a single device, you divide them by the number of devices, and then you do that for all of the devices, and all of the devices will have the same state now, if that makes sense. But less important for now. Let's focus on the loss scaling. Multiply grad. So let's see what's going on here. Okay, so what we do is we divide, so we have this multiply grads, and we divide, this is 1 divided by 128. The reason we divide by 128 is because NLL loss had, as a reduction method, had a sum. And because we had 128 elements, we now want to divide by 128, if that makes sense. So let's enter here. Let's see what's going to happen here. So multiply grads. So we just take that multiply factor, which is now 1/4, because we want to do the unscaling of gradients, and we additionally multiply by this 1/128. This is the C constant. That's that number, and then that's gonna all aggregated inside of this variable, and we're gonna later apply that variable to actual gradients. We'll see that a bit later. Okay, let's exit here. Now gradient clipping is gonna happen. Again, I will have to skip this part, but okay, no, actually, let me quickly enter it. Let me see what's going on there. I think it's kind of fairly intricate. There is a lot of, as you can see, a lot of steps, but I think there might be a part that's kind of interesting for us. Oh yeah, there is. So here is the multiply factor. Here's where it comes into the picture. So we basically grab the gradients of our, we grab the norm of the gradients, and then we multiply that by the multiply factor. And that's kind of an optimization detail, because you didn't have to multiply the actual gradients. You just took the norm and then multiply by this factor, and you get the equivalent result. That's kind of neat. Okay, let's see what's going on here. Let's continue here. Max norm, grad norm. And again, we have another multiplication for the multiply factor. Why? Because the gradients were, the norm was 16, but we want to clip it to 1. And that means we have to take this number and multiply with that number of gradients, and then they will obey this property of having gradient norm of 1, if that makes sense. That's why we have another multiplication. So now the multiply factor has 3 things going on. We have the loss unscaling, we've divided with a sample size, and finally we've divided by this ratio of the norms. Let's continue. We check some overflow, again, a bunch of details, and let's continue. We check the grade norms. Let me see what this is. I think this is just gonna be skipped. So yeah, it's just skipped. Okay, now we make sure that we don't have, none of the values in the grads are infinite. So if we had nans, then this exception would be raised, and it would be caught in this particular context here, where they have the nan detector that kind of, let me show you what it does. So nan detector, blah, 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 it basically is going to capture some of the values so that we can debug it later on. Detects the first nan or in forward and or backward pass and logs together with the module name. Okay, so it's just gonna help her to debug where the nan occurred. And then once they do that, they do another forward pass here under that context, and it's gonna catch the first nan. So they say here, rerun the forward and backward pass with hooks attached to print out where it fails. Okay, so that's kind of how they cope with the errors. Let's finally enter the optimizer step. That's where we're gonna finally apply that multiplier, the famous multiplier. So let me show you here, step, step, step. Let's continue here. Okay, unscale grads, so let's see what it is. I think that's gonna be our logic. So here we are. We enter this part, multiply grads with the multiply factor. Okay, that's finally the moment where we apply the multiply factor and then we reset it back to 1. And then the whole procedure will continue. So here you can see here, we just go through the parameters and we multiply the parameter, the gradient associated with that parameter, with that weight, data, and then multiply by C, and C is the multiplier we were accumulating over time. So we had 3 factors again, if you recall. The sample size, the gradient unscaling, and finally the ratio of the norms. I'm gonna step out of this, so hit this step out arrow, and we are done. We are done here. We've done the stepping. We update the scaler. So the scaler is gonna do what? Okay, nothing interesting here. We can exit all of this, and we are back to our train step in the trainer. We just debug some information, we didn't have any nuns, and that's pretty much it. So I think I can skip all of this. A lot of details. Yeah, go at your own pace, explore this code if you're curious to learn more. But I think we saw most of the interesting parts. So let me just do this. Let me see why we are, okay, so I'll just have to put breakpoint there, hit F5, here we are. So as you can see, we're finally back in the train.py file, and we are inside of the train function here. Let me see whether there is something interesting. End of epoch. We're gonna just skip this part. Nothing's gonna happen. It's gonna be a no up. If we should stop, and for now we are not stopping, so that means we are again gonna fetch the next samples and continue this whole loop, and that's it. So we're just gonna keep on doing this training, guys. That's it. You hopefully saw what it takes to build these LLMs. We did exclude the whole distributed part of the equation, which is probably the hardest part. So like doing the model parallelism, the data parallelism, the pipeline parallelism, all of that. goodness. And then there is the zero optimizer where you do the partitioning of the activation. So there is so many details. Again, we also skip the checkpointing. So like, yeah, tragic. Cool, I'm gonna stop here. Let me know, please let me know whether you like this video. Depending on that, I'm gonna probably modify the videos I'm gonna be creating, because by doing this, I learned a lot, and so I thought just kind of walking you through the learning, so it didn't feel like a big of an effort. But like going forward, I'll probably won't be doing this unless people find it useful. So do let me know down in the comments whether this was actually interesting and useful for you. Having said that, if you like this video, please share it out. That's the best way you can support this channel. Also subscribe to this channel if you haven't already, and see you next time.